Hello, very good morning to all, and welcome to my class. Today we are going to discuss about the P block elements, right? So far we covered almost, half of the syllabus we already covered. So in today class we are going to see P block elements, right? So we classify P block elements into two class. Today, in first class, we are going to cover all the important concept related to this chapter. And in the next class, we are going to solve some PYQ questions that were coming in your advanced paper, right? So let's start with the today's session. Before this, I just want to know whether my voice is audible to you or my screen is visible to you or not. If you face any problem related to this, you can text me, right? So let's start with the today's session. This session is going to be very, very important, right? Because very important questions were coming from this P block chapters. So this chapter is very important in a point of if we're talking about the inorganic chemistry part. So P block play a very important role. Lots of questions were coming from this chapter directly. So you must understand the concept so that you can able to solve the question related to this chapter, right? So let's see. Before starting the chapter, I want to, discuss about the P block elements position in the periodic table, right? So this is the periodic table as we can see in our first slide. We have a P block elements, right? From group 13, yeah, that is from group 13 and this is group 18. So we have a six group which lie on the P block, right? These six group are known as P block element. The first group is a boron family. The second group is a carbon family, and the third, that is 15 group is a nitrogen family, oxygen family, fluorine family, and the neon family. So these six group that we are going to discuss in detail way. Okay, so first of all, you should must write the each and every name of the element of this P block group because these are very important because many times questions will come when instead of aluminum when they are given TL or EN, then you're getting confused. EN and TL belong, indium and thallium belong to which group? So better you learn the periodic table in a detail so that you won't face any problem related to this, right? For example, group 13, we can remember like group 13, like that is boron, aluminum, gallium, indium, and thallium. Similar for the group 14, we have a carbon, silicon, germanium, tin, and lead. Similar group 15, we have a nitrogen, phosphorus, arsenic, antimony, and bismuth. Similar group 16, we have a oxygen, we have a sulfur, selenium, and tellurium, right? And polonium. And the 17th group, we have a fluorine, chlorine, bromine, iodine, astatine, right? So these elements you must remember so that you can easily solve the question related to this. So now we are going to discuss group 13. Then after group 14, 15, 16, 17, and 18. So we are going to cover entire P block element in this class, right? So let's start with the group 13 element. So what are the some basic characteristics of group 13 element, right? So what are the some basic characteristics of group 13 elements are? Basically, it is a boron family. So basically, group 13 is also known as a boron family. And the member of this group is, we already discussed, that is boron, aluminum, gallium, indium, and thallium, right? Now, if I'm talking about the basic properties like their size and all these things, so we know that down the group, when you move from boron to thallium, there is increase in the number of shell. So obviously size increases down the group. So there is no exception in this. In this slide now, we are going to discuss only those cases in which some exceptions are there, some important properties are there related to their physical or chemical properties. So only those properties that we are going to discuss, not all entire basic web properties, because these properties we assume that we already know this thing, right? And whenever you need, I'll explain this thing. No worries for that, right? So basically, if I'm talking about the size, what is the size? Then we know that any group in the periodic table, when you move from top to bottom, definitely size increases due to increase in the number of shell. So definitely boron, aluminum, gallium, indium, and thallium. So in size, there is one exception is there because we know that if I'm talking about the size must be like that is boron, aluminum, gallium, indium, and thallium, right? But there is exception between aluminum and gallium, right? Expected and actual. So actual order is like aluminum having greater size as compared to gallium. So this is the small exception here. Why this is? So this is due to the poor shielding effect of the gallium, right? So this is due to the shielding effect. So remember this shielding effect of the gallium due to the addition of 3D electrons, 4D electrons, and 4F comes into the picture. And due to the poor shielding effect, aluminium are slightly bigger than gallium. So there is exception in this, right? So on the similar basis, if I'm talking about the ionization energy, then there is also a you know there is some sequences like if I'm talking about the first, second, and the third ionization energy, then obviously the general electronic configuration. What is the general electronic configuration of this element? It is nothing but that is NH2 and NP1, right? So NH2 and NP1. So we can say that their first ionization enthalpy is very, very, compared to the second, the first ionization enthalpy is low. So here it is mentioned the first ionization enthalpy of this element is very low because the element you have to remove the electron from the outermost shell of one electron only, right? So we can remove this electron very easily. Now if you talk about the second ionization enthalpy, then you have to remove the electron from the innermost or shell, or we say NH2, which is fully filled configuration. So we require more amount of energy, right? So there is a large difference between the first and the second ionization enthalpy, because for the removal of second electron, you have to remove electron from the stable one, that is NH2 electronic configuration, right? So there is a very large difference between the first and the second ionization energy, right? Similarly, if we talk about the third ionization enthalpy, then definitely it will be greater than the second ionization enthalpy, right? So, but not so much large as compared to first and second. So this point you must remember, that is member, atomic size, general electronic configuration, and based off this ionization energy as well, right? Now, melting point. So if I'm talking about the melting point, so melting point decrease from boron to gallium and then increase up to the thallium. So first it decreases, that is boron is very hard and it possesses a high uh, it was a very high melting point as compared to gallium. Aluminium also possesses good melting point, and for gallium the melting point is decreases. Now again from gallium, and there is an increase in the melting point up to the thallium. So just remember this break here, that is from boron to gallium it value melting point is decreases, and from gallium to thallium again melting point increases, right? So this is the melting point order of the group 13 elements. So I hope this is clear to you. Right. Okay. Now, if I'm talking about the metallic character, so increase from boron to thallium because boron is a non-metal and thallium is a metal. So we can understand this thing, that is a metallic character, it decreases down the group, or just opposite of the metallic character, that is a non-metallic character, which is increases as we move along up toward the top of the group. That is, the boron is the most non-metallic as compared to, and thallium is the least non-metallic. Or if I'm talking about the metallic character, just reverse of this. Okay. So these are the some basic properties of the boron family, like size, ionization enthalpy, melting point, metallic character, and ionization energy. Now, let's move to the some important compounds of this family. That is, first we are going to study the boron. That is, how will you prepare this boron, right? So preparation of boron, that how will you prepare boron and all this thing, right? So let's see how will you prepare boron and all. So basically, for the preparation of boron, we need boric acid. So from boric acid, as we also prepare boron, right? So how will you prepare boron from the boric acid? Like when the B2O3, they react with the 3 magnesium, it will form 2B plus 3 MgO, right? So from the boric acid, that is B2O3, this react with the 3 Mg, so it will form 2B plus 3 MgO, right? Now, so this is the from the boric acid, that is B2O3 plus 3 Mg, it will give 2B plus 3 MgO. Similar from the boron trichloride, that is at 1270 Kelvin, when the 2BCl3, that is the boron trichloride at 1270 Kelvin react with hydrogen gas, it will produce 2B plus 6HCl, right? So from this also we can prepare this boron, right? So that is BCl3 plus 3H2, this will also prepare boron plus 6HCl. I hope this is clear to you. Right. Now, at 900 degrees Celsius, when BCl3 react with the zinc, it will also produce boron plus ZnCl2 solid, right? So this is how we actually prepare boron. So first method is from the boric acid, and the next method is from the boron trichloride. So this is the way by which we can prepare boron, right? Next. By electrolysis of the fused mixture of boric anhydride B2O3 and magnesium oxide, that is MgO, and magnesium fluoride at 1100 degrees Celsius. So we can also prepare by the electrolysis of fused mixture of boric anhydride B2O3 and magnesium oxide, that is MgO, and the magnesium fluoride at 1100 degrees Celsius, right? So by this we can also prepare this. Now, how will you prepare? Like this, if we have a 2 MgO, this will react to give 2 Mg plus O2, and this B2O3 is react with Mg to form boron. So these are the some method by which you prepare boron. The first one is from the boric acid, the next from the boron trichloride, and the next is by the electrolysis of fused mixture of boric anhydride and magnesium oxide. So magnesium fluoride at 1100 degrees Celsius, we can prepare this. So I hope this is clear to you. How will you prepare boron from this following compounds? Right. Now we are going to discuss some important compounds of boron. So what are the some important compounds of boron? Because this is going to be very important on a point of view, questions point of view. Many of the questions will directly come from this topic, right? So let's see how will you prepare this thing and all. Okay. So how will you prepare this thing? So we know that if we're talking about the compounds of boron, so orthoboric acid, this play a very important role. That is a orthoboric acid. So what is this orthoboric acid and all? And how will you prepare this? So basically, preparation of orthoboric acid, it will prepare from either borax or colemanite, right? So these are the two way by which you can prepare orthoboric acid, right? By from borax or for colemanite. For example, how will you prepare from borax? So we know that formula of borax is nothing but this is Na2B4NO7. So Na2B4O7 is the formula of borax. When this borax is treated with H2SO4 and water, you will get Na2SO4, that is sodium sulfate, plus H3BO3, that is a boric acid, orthoboric acid we can say. So by this way we can prepare orthoboric acid. The first method is borax. Always remember this. What is the formula for the borax? That is Na2B4O7. And how will you prepare orthoboric acid from this? By treating borax with the H2SO4 and water. So we can prepare. Now, same, how will you prepare from the colemanite? Colemanite having formula C2, calcium 2, right? B6 and O11. When they are treated with the SO2 and water, it will produce the orthoboric acid, right? So these two methods by which you can prepare the orthoboric acid. So this must remember, you must remember this two process name, right? That is from borax and from colemanite. So these two are the methods by which you prepare orthoboric acid, right? Now, move to the next thing, that is what is the properties of orthoboric acid. So this play a very important role. That is what is the property of the orthoboric acid. So first is action of heat. When you heat boric acid, just remember this, when you heat orthoboric acid, that is H3PO3. Now when you heat this, let us assume at 100 degrees Celsius, or we say 373 Kelvin. So water molecule remove and it will convert it into metaboric acid. It will be converted into metaboric acid. Okay. So the orthoboric acid is converted into metaboric acid. Again, when they are heated with the 413 Kelvin, again there is increase in some temperature. Then again a water molecule decreases, release out, and it will convert into H2, and this is nothing but B4 and O7. This is known as tetraboric acid. So this is known as tetraboric acid. So this is known as tetraboric acid. Now again when you heat this, again in a final step, when you heat, again elimination of water molecule takes place and you will get B2O3, or we say boron trioxide. Always remember this thing, that is boron trioxide. Clear है सबको? ठीक है? So this is how we can actually prepare this, right? So I hope this is very much clear to you. That is how will you prepare this, all these things. Okay, good. So these are the important properties, or we say action of heat on the boric acid. So when you heat orthoboric acid, it will convert into metaboric acid. Again, when you heat metaboric acid, it will convert it into a tetraboric acid. Now, when you treat this tetraboric acid, it will be converted into boron trioxide. So just remember this sequence. This is very, very important sequence, right? Because questions are coming directly when they ask what happened when the orthoboric acid is heated. So what you will get, whether metaboric acid. Now again, when they are heated, what you will get, that is a tetraboric acid. Now again, when they are not heated, then what you'll get, that is a boron trioxide. So boron trioxide is the final product that we get. Okay, so I hope this is clear to you. This one will play a very, very important role. Now, the next thing is that is a weak monobasic acid behavior, right? So the weak monobasic acidic behavior. So what do you mean by this? Is weak monobasic acidic behavior. We are talking about the orthobaric acid, right? So basically BOH3, that is H3BO3, it will give H plus H2, right? Thus on titration with NaOH, it gives sodium metaborate salt. So it behave like a weak monobasic acidic behavior, right? So when they are treated with the NaOH, it gives sodium metaborate salt, right? Now, reaction with the metal oxide. So what happened when the orthoboric acid is treated with the metal oxide? So whenever the meta orthoboric acid, that is BOH3, we can also write as BOH3, right? It will become same, that is nothing but again this will become H3, right? And this is B and O3. So both things are same. So we can write orthoboric acid as BOH3. Both things are same. So now what happened when the BOH3, that is a orthoboric acid, when they are treated with the metal oxide, that is MO. So what will they form upon fusion? They form M borates, right? They form M borates. Always remember M borates, where M stands for the any bivalent atom. Either it will be a magnesium or we say calcium. So any bivalent at metal, right? So it will form metal borates. Clear है सबको? Right. So this is what we'll get when you reaction of the metal oxide with the orthoboric acid. Now, next with reaction with ammonium bromofluoride. So what you will get, that is when the reaction of ammonium borofluoride. So when this is treated with ammonium boron fluoride, you will get this compound like BF3, right? So you will get the compound like BF3. So this is known as ammonium borofluoride. This is ammonium borofluoride, this one, right? So when the orthoboric acid is heated in presence of NH4HF2 fusion, it will convert it into ammonium borofluoride. Now, ammonium borofluoride is react with B2O3 at presence of heat to give BF3, right? Which is behave as a Lewis acid. So I hope this is clear to you. That is how will you prepare orthoboric acid. So we have a two method of preparation of orthoboric acid, either from the borax or from the polyamide, right? Either from the borax or from the polyamide. And the properties of orthoboric acid, like when the action of heat, now when this is heated, then the orthoboric acid is converted into the metaboric acid. Metaboric acid is further converted into the tetraboric acid, and this tetraboric acid is converted into boron trioxide, right? So this is all about the compounds of boron, or we say orthoboric acid, and the of this thing, right? So I hope this is clear to you. Now, the next compound is after orthoboric acid, we have a next term is borax. That is a sodium tetraborate, or we say Na2B4O7.10:2. So how will you prepare borax? So basically, we prepare borax from the boric acid. In the previous case, we prepare boric acid from borax. Now we are preparing borax from the boric acid. So what happened when the boric acid is treated with Na2CO3, right? When the boric acid is treated with Na2CO3, it will form Na2B4O7 and 6H2O plus CO2, right? So when there's the boric acid, that is H3BO3, and when they are treated with Na2CO3, it will form Na2B4O7, that is a borax. So the formation of borax will take place. So the first method is from the boric acid. So we prepare borax from the boric acid itself, right? Now, What are the properties of borax? So if I'm talking about the properties of borax, then how borax behave? So if I'm talking about the basic nature, so the aqueous solution of borax is alkaline in nature due to its hydrolysis. So the aqueous solution of borax is basically basic in nature, always alkaline in nature due to its hydrolysis. When Na2B4O7 in hydrolysis, it will form a sodium borate, that is NaBO2 plus boric acid. Now this sodium borate again react with H2O to form NaOH and boric acid. So the formation of this NaOH will show that the aqueous solution of borax is alkyl in nature due to its hydrolysis, because their hydrolysis is easily takes place. Now, action of heat. So just like when we heated, boric acid will get metaboric acid, tetraboric acid, and boron trioxide. So what you'll get in case of borax? So when the borax is heated, it will convert it into Na2B4O7, 10 water molecule will be removed. And further, when they are treated at 740 degrees Celsius, it will convert it into a sodium NaBO2, right? NaBO2, that is sodium borate, and boron trioxide will be formed also, right? So this is against the action of heat of the borax, right? The next important compound of the boron family is the diborane, right? So diborane is the next important group of this family, B2S6. So how will you prepare diborane with prickly beta? So the diborane we can prepare by the reduction of boron trifluoride. So BF3, when they are reduction with BF3 in presence of LiLH4, it will produce B2S6 and LiLF4, right? Now from NaBH4, we can also prepare by treating with H2SO4, that is B2S6. Now B2S6 important point here, that is what is the structure of B2S6. So here we can say that this is B and this is H, this is again H, this is H, right? This is again H, this is H, this is H. So how will the B2S6 will form? Because we know that boron having only 3 valence electrons, so it is capable of forming only 3 bonds with the hydrogen, not more than this. Because in B2 in Al2Cl6 Al2Cl6, the bond between the Al and Cl is coordinating bond, because Cl having lone pair of electron, so it can donate both of the electron to the aluminum. But in this case is also not possible, because hydrogen have only 1 electron, and through this 1 electron they already form the bond. So how B2S6 will form? So basically, B2S6 will be like a structure like this, right? Structure like this. So what will this? This will form a this is something like banana structure, right? This is something like banana structure, right? So they will form like a banana structure. This means here we have a 3 center and 2 electron bond, right? 3 center, 2 electron bond. What do you mean by this term 3 center, 2 electron bond? Here we can say that B, H, and B. So total in this boron, hydrogen, and boron, we have only 2 electrons between these 3 centers. Similar in the downward boron, hydrogen, and this boron, we also have a 2 electrons between the 3 centers. So this is called 3 center 2 electron bond, where this type of bond is called 2 electron 2 center bond. Right. So in B2S6, we have a structure like this in which the 3 center 2 electron bond exist. And due to this, their bond length is also increases. If I'm talking about the terminal BH, if I'm talking about the bond length, right, bond length of the terminal boron hydrogen, that is the terminal one, that it will having a more bond length as compared to this bridge, right? So lesser bond length, sorry. So if I'm talking about the bond length between the terminal boron and hydrogen and the bridge boron and hydrogen, so bridge boron and hydrogen having the bond length more than this. So please try to consider this thing, right? I hope this is clear to you. You have a no problem related to this. Just wait for a minute. Wait. ठीक है बेटा? So this is how will you actually prepare this thing, right? So I hope this is clear to you. Okay, so this is how will you actually prepare. This is what the structure of the diborane. So diborane consists of a 3 center 2 electron bond as well as 2 electron 2 center bond. If I'm talking about the bond length of boron hydrogen, then in case of terminal, this one BH, this will be shorter, and the bridge one is a longer bond length of boron hydrogen as compared to this terminal bond length, right? So this is all about the structure of the diborane. Okay. Now, what is the properties of diborane? So basically reaction with water. So when the diborane is treated with water, it will form boric acid like S3BO3 plus 6H2. Similar combustion reaction also shown by the diborane. When the B2S6 is treated with O2, it will form boric acid plus H2O. And a good amount of heat is also released like 26.1, 2615, 2615 kilojoule per mole heat will be released. So it's a very good amount of heat that will be released when the combustion of boron higher diborane takes place, right? Now we are going to study some compounds of aluminum, right? So these are we already discussed the compounds of boron. So which compounds of boron we already discussed, beta? That is, first of all, we are discussing about the orthoboric acid. Later, we are discussing about the borax, and then last we are discussing about the borax, orthoboric acid, and the diborane. That is B2S6. So these three are the important compounds of the boron. Now, let's see some compounds of aluminum as well, right? So let's see some compounds of aluminum. So basically, aluminum oxide, or we say alumina, that is Al2O3. So what are the compounds of aluminum? So first one is aluminum oxide, that is Al2O3, or we say alumina. We can also call Al2O3 as a alumina. So how will you prepare Al2O3? So we can prepare Al2O3 when the aluminum hydroxide is heated, then we'll get Al2O3. Similar, when the aluminum sulfate is heated, then we also get Al2O3. Similar, when the ammonium aluminum sulfate 24H2O, this will also dissociate to give Al2O3. So this is all the structure. This is the method by which you obtain Al2O3. Now, this is the structure of aluminum chloride. So it is very much similar to the B2S6. Just difference is that in case of B2S6, boron having capability of form only three bond because it having only three valence electron, not more than this. On the other side, hydrogen has only one electron and it cannot form more than one electron. So what option we left is we can make a three center two electron bond like this. But in this case, we know aluminum also belong to the boron family, so it have also only three valence electrons, so make only three bond. But here, one thing which is different from the diborane is here, in place of H, we have a chlorine. So we all know that chlorine having seven electrons in their outermost electron. So out of these, right? So out of these seven electron, chlorine is left with, after forming one bond, they will left with the six more electron. So out of these four electrons are there, and here they will form the coordinate bond. Coordinate bond means what, beta? Coordinate bond means coordinate bond. So what do you mean by this coordinate bond? So coordinate bond means nothing, but here it will give two electrons of only in this bond, two electrons of chlorine will be present, right? So coordinate bond is different from the covalent bond in a such a way that in covalent bond, two bond is formed between the two atom and sharing of electron will be takes place. But in coordinate bond, one single atom can donate their own electron. Right. So these are called coordinate bonds. So here aluminum in this bond coordinate bond, there is no electron of aluminum involved in this bonding. So there is a total two electrons of chlorine which will take participate in this bonding. Here also this chlorine can also form coordinate bond this with aluminum. So here we can form the dimer like AlCl3 become Al2 and Cl6. So I hope this is clear to you. That is what is the difference between this B2S6, that is the diborane, and the Al2Cl6 diagram, right? Now, so what is the properties of aluminum chloride? So can you suggest some properties of aluminum chloride? So first is it is a white and hygroscopic solvent, means moisture absorbing solids, right? And it sublimines at 180 degrees Celsius. It form addition compound with NH3, PH3, and calcium chloride. Sorry, COCl2, right? That is cobalt chloride. So form addition compound with the NH3, PH3, and COCl2. It hydrolyzes, right? So it hydrolyzes to give again aluminum hydroxide. Again, action of heat. So what happened when action of heat takes place? So again, action of heat. This AlCl3 will convert into AlOH3 and Al2O3 plus 6 right? So these are the hydrolysis and action of heat property of the aluminum chloride. So this is all about the group 13 element. So I hope this is clear to you, right? About the group 13 elements. Everything is clear related to group 13 elements. Let's quickly revise this thing. In group 13 element, first we have discussed about the basic properties like melting point, members of the group, ionization enthalpy, size, metallic character. Then we are study about the method of preparation of boron, that is from boric acid, from boron tetrachloride, and by the electrolysis fuse of mixture of boric and hydride. Later we are studying this, that is a compound of boron. So compound of boron, basically that is orthoboric acid, which is very important, which will you prepare from the borax, or we say colemanite. And the next we study, that is the properties of orthoboric acid, that is against the action of heat, which is very, very important. When the boric acid is treated, it will convert it into metaboric acid, tetraboric acid, and the boron trioxide. Now, some reaction like a weak monobasic acidic behavior, reaction with the metal oxide, reaction with the aluminum borofluoride. Now, the next property that is studied in the group 13 is, that is the borax. So the borax is nothing but sodium tetraborate, and preparation of boric acid from the preparation from the boric acid, that will prepare borax from the boric acid, and just opposite we will prepare boric acid from the borax as well. That we are talking about their basic nature and the action of heat. That is what happened when the borax is heated. So whenever the borax is heated, it converted into Na2B4O7, and again when they are heated, it converted to B2O3, right? That is sodium borate and B2O3. Now, in the next, we are discussing about the diborane, that is the preparation of diborane from the BF3 and NaBH4. Similar the structure of the diborane, we have a structure like three center, two electron bond, right? And the reaction with water and the combustion, they emits a good amount of energy. Similarly, we will study about the compounds of aluminium, that is aluminum oxide or alumina. We can prepare by heating aluminum hydroxide, and the structure of aluminum chloride, and some physical properties, right? Now, so we are covered already group 13 elements. So on the similar basis, we are going to cover group 14 elements as well, right? So just give me 2 minutes, let take some water, and then we're going to start group 14. Right now, let's study about the carbon family, that is the group 14 elements, right? So basically, group 14 elements include that is the member of the group 14 element like carbon, silicon, germanium, tin, and the lead, right? So these are the carbon family. They are having group 14 elements. So we have a carbon, silicon, germanium, tin, and lead. So this group is play a very important role in the semiconductor because the germanium and the silicon, these two elements play a very important role in the making any semiconductor devices. So in almost many applications of semiconductor which are made up of silicon and germanium itself, right? So these property are this group play a very important role, right? So let's see some general feature for this group as well. So if I'm talking about the atomic sizes, then again similar to like previous group and all other group, or we moving down the group as the increase in the number of shell takes place, so the size also increases from carbon to lead, right? Now, similar ionization enthalpy, so it decreases from carbon to Sn. So first ionization enthalpy decreases because the size increases and then increase up to Sn to Pb. Why this is happening? So this is basically due to the inert pair effect, right? That the D and F electrons comes into the picture, they provide a shielding effect, and due to this will be happening. Now, if I'm talking about the metallic characters, so carbon and silicon are the known metal. Germanium is the metalloids basically, and Sn and Pb are the metal. So this group include both metal, non-metal, and metalloids, right? So the carbon and silicon, these two are the basically a non-metal, and germanium is a metalloid. We can also call silicon as a metalloid, right? Because silicon having also some tendency to behave like an semiconductors, and Sn, that is tin and lead, there are the metal. Now, catenation property. So they show catenation property, that is carbon and silicon show a tendency to combine with its own atom to form a long chain polymer, right? So carbon and silicon show a tendency to combine with its own atom to form a long chain polymer, right? So these are the catenation properties. So this point you also remember, okay? So it is very much clear to you that is what is ionization and what is ionization energy, what is the member of this group, what are the size, what are the metallic character, and what is the catenation. So carbon and silicon show a tendency to combine with its own atom. So basically catenation property refers to the self-linking property, right? Self-linking properties is also known as a catenation property. So carbon and silicon show a tendency to combine with its own atom to form a long chain polymer, right? Now, so some important compounds of carbon. So what are the important compounds of carbon? So the first important compounds of carbon is carbon monoxide. So what is the, how will you prepare carbon monoxide basically? So by heating carbon in the limited supply of oxygen, right? So by heating carbon in a limited supply of oxygen, that is when C is heated with half O2, it will form CO. So by heating carbon in the limited supply of oxygen, we'll get the CO, carbon monoxide. Similarly, by heating oxides of the heavy metal like iron, zinc with the carbon, we'll also get the carbon monoxide, right? So this is the method by which you prepare carbon monoxide, by heating carbon in the limited supply of oxygen and by heating oxides of the heavy metal like Fe2O3 and zinc oxide. Now, another way for preparing carbon monoxide is by passing steam over a hot cup. So if you passing a steam very high superheated steam, superheated water, that is steam, over a hot coke, that is a very a very hot type of carbon, you'll get a CO plus H2, or commonly known as water gas. So this phenomena is also known as syngas, or we say water gas, because this method is also used for the synthesis of methanol. So that's why they are also known as syngas or water gas reaction, right? Now, by passing air over a hot cock, that is 2C plus O2 and N2, it will also produce CO plus N2. This is known as a producer gas. So it is also known as producer gas. And the upper one is known as water gas. CO plus H2 is known as water gas, and CO plus N2 is known as producer gas. Always remember this thing, right? Now, properties of carbon monoxide. So basically a powerful reducing agent, Fe2O3, and they react with CO. So basically CO acts as a very good reducing agent. So it acts as a powerful reducing agent like Fe2O3. It reduces Fe2O3 to Fe, right? And converts CO to CO2. Similarly, it reduces copper oxide to copper. So it is a very powerful reducing agent. Burn in air to give heat and carbon dioxide. So it will burn in air, like when CO is treated with half O2, it will convert it into CO2 plus heat. So these are the some basic properties of the carbon monoxide. First is it behave like a powerful reducing agent, like it reduce Fe2O3 into Fe, copper oxide into copper, and it react with oxygen to form CO2 and emit large amount of energy as well. Now, test for the carbon monoxide. So how will you test whether this gas is a carbon monoxide or not? So basically burn with the blue flame. So they carbon if the gas contain carbon monoxide, so they burn with the blue flame. They turn filter paper soaked in a platinum or palladium chloride to a pink or green. So they turn the filter paper which is soaked or which is absorbed in the platinum and palladium chloride into green and pink. So these are the tests for the carbon monoxide, right? Now study the carbon dioxide. So let's the next compound, that is the carbon dioxide. So how will you prepare this carbon dioxide beta basically? So basically the preparation of carbon dioxide, that is by the action of acid on carbonates, that is CaCO3, when they react with the HCl, it will form CaCl2 plus H2O. So carbon dioxide, we can prepare carbon dioxide by the action of acid on the carbonate, like when the calcium carbonate is treated with the 2HCl, or we say the when the sodium carbonate is also, then we'll get the CO2, right? So the by action of acid on the carbonates, again by combustion of carbon. So this is a very simple reaction. We already know when the incomplete combustion takes place, then the carbon monoxide will form. And when the complete combustion takes place, then the formation of CO2 will be formed, right? So this is the another method for producing carbon dioxide. Now, what are the properties of carbon dioxide? So basically, it turns lime water milky, and this reaction is very famous. When the calcium hydroxide is treated with CO2, it will be converted into CaCO3, right? So it turns lime water into milky. Now, milkiness disappear when the CO2 is passed in the excess. So this milkiness disappear when the CO2 is passed in the excess. So if you take more amount of CO2, then this milkiness disappear, because when the more amount of CO2 will treated with CaCO3, it again convert this into the calcium hydrogen carbon, right? So this is one is very important rule. The first property, it turns lime water, that is calcium hydroxide, that is also called slake lime, into CaCO3, that is the lime water, right? So it turns lime water milky. So the formation of milkiness will take place. Now, if you take the excess of CO2, then again it convert this milky calcium carbonate into calcium hydrogen carbonate. This point you must remember. So this is the important notable point here. Okay. Now, solid carbon dioxide, we also known as a dry ice, is obtained by cooling CO2 under a pressure. It passes from the solid state to a gaseous state without liquefying, hence it is called dry ice. So why they are called dry ice? Because it converts directly from solid state to the gaseous state without converting into the liquid state. That's why they are called dry ice. Right. So this play a very important role. This one play a very important role in many of the things. Right. So try to understand this thing. Right. Okay. So this is how we can prepare this. So this is the milkiness disappear. So basically, yes, we are talking about the dry ice, right? So basically, dry ice are used, in the transportation and the storage of the food materials. Like if you want to um, store the food for the long time. Then we use dry ice in the shipment of the fishes and any raw material from one country to another country. So we can use this dry ice because it will directly convert from solid to vapor. So there is no problem of liquid on all. If you use the normal ice, then this liquid will be formed. So in this, there is no issue of this, right? So it turns lime water milky, the first point. Milkness is disappear if you use the excess of CO2. Solid carbon dioxide, or we say dry ice, is obtained when you cool CO2 under a high pressure, right? So when you cool CO2 gas under a very high pressure, then the dry ice will be formed. It passes from the solid state to the gaseous state without involving liquid state. That's why they are called dry ice. Right. So I hope this is clear to you. Now we are talking about the carbide. So what is this carbide is all about? What is this carbide? So basically the salt-like carbide. So these are the ionic salt containing either C2 twice negative, that is acetylide ion, or C4 negative, that is methanide ion, right? So carbides basically, so they are salt-like carbide. So these are the classification of carbide. So either we have a salt-like carbide. So basically these are the no, these are the ionic salt containing either C2 negative acetylide ion or C4 negative methanide ion like CaC2, Al4, C3, and B2C. So they are the carbides, right? They are the salt-like carbides. Now the covalent carbides are these are the carbides of non-metal such as silicon and boron. So in such carbides, the atom of two elements are bounded to each other through a covalent bond. That is SiC is also known as carbodum, right? This is also known as a carbodum. So basically, a salt-like carbides means they are the ionic carbides. Covalent carbide means they are the carbides of the non-metal, right? Now, interstitial carbide means so these are the formed by the transition element and consist of a metallic lattice with the carbon atom in the interstice. That is tungsten carbide, vanadium carbide. So we have a three types of carbide. The first one is the salt log carbide. So these are the ionic salt containing either C2 twice negative acetylide ion, C4 minus negative methanamide ion, right? And the covalent carbides. So these are the carbides of the non-metal of silicon and boron, and the interstitial carbide like a tungsten and the vanadium carbide, right? So this is all about the carbide, what you have. Now, so this is all about the 14th, no. Yeah. So now we are studying the compounds of silicon. So compounds of silicon play also a very important role, like a sodium silicate. This is the first compound, that is a sodium silicates. So basically they are prepared by the fusing soda ash with the pure sand at a high temperature. So how will you prepare sodium silicate? So we can prepare sodium silicate by the fusing soda ash with the pure sand at a high temperature. Like when you treat Na2CO3 and SiO3, it will produce Na2SiO3 plus the CO2. Now, silicon, that is a silicon polymer containing SiO. So now we're talking about the silicons. What is silicons? So silicon polymer containing SiO-Si linkage formed by the hydrolysis of alkyl or aryl substituted chlorosilanes and their subsequent polymerization. So what is silicate? So salt of silic acid H4SiO4 comprised to SiO4 negative unit having a tetrahedral structure form as a result of sp3 hybridization. So they are known as silicates. So in silicates, we have a hybridization of sp3. So this is all about the group 14 elements. Let's quickly revise group 14 elements that what we have studied in this. So first is we study the general characteristics, general uh, properties of this element, like their members, ionization enthalpy, metallic character, and catenation property. And the next we will study about the compound of carbon, that is carbon monoxide, its property, that how they are act as a good reducing agent, and how they prepared. So this we study about the carbon, how will react with the oxygen. Now in the last we study about the test for the carbon monoxide, like it burn with the blue flame, turns the filter paper soap with platinum and palladium into pink or green. So this property we already studied. Now next we studied about the carbon dioxide, right? So what is this carbon dioxide? So basically in carbon dioxide, preparation of carbon dioxide, so by the action of acid on carbonates, that is to prepare carbon dioxide by the preparation of carbon dioxide. How will you prepare carbon dioxide? By the action of acid on carbonates. Like whenever the calcium carbonate, magnesium carbonate is treated with HCl, it will produce CO2. By the combustion of carbon in the excess supply of oxygen, then you will also got CO2. Now, properties of carbon dioxide, it turns lime water into milky. If we use the excess of CO2, then again it will disappear this color. Solid carbon dioxide is also known as dry ice because it obtained by cooling CO2 under a high pressure. it passes from the solid state to straight to the gaseous state without converting into the liquid. That's why they are also called dry ice. Then we studied about the carbides. Like carbides, three types of carbide we have. Salt like a high carbide, basically formed by the ionic compounds. Covalent carbide, basically formed by the non-metals, and the interstitial compound formed by the D block element like a tungsten and vanadium carbide. Right. Then the last we studied about the compounds of silicon like a sodium silicate, silicons, and silicate. So in silicons, silicon oxygen and silicon linkage is present, and the silicate salt of silicylic acid and having tetrahedral geometry and sp3 hybridization is possible in silicates. Right. So this is all about the group 14 elements. So I hope this is clear to you. That is what is group 14 elements and all important properties related to this, right? Good. Okay. So let's study about the nitrogen family. That is what about the nitrogen family and what is this? So basically, nitrogen belong to the group 15 of the element, and this element play a very important role because it consists of nitrogen, which are used in the making of many of the compound like HNO3, like ammonia. So these their compound play a huge impact on our society, huge impact on our agriculture, right? So these elements are very important to study because their compounds are mostly used by us in our day-to-day life, right? So these are the important ones. Right. So group 15 element basically consists of nitrogen, phosphorus, arsenic, antimony, and bismuth. So these five are the basic element of the group 15. Now, just like any other group, their atomic radii also increased out the group. But if I'm talking about to AS to BI, there is a very small increase from AS to BI, and it is due to we know that it is the when the 4F and 5F and 5D electrons comes into the picture due to their shielding effect, right? Poor shielding effect of this 4F and 5D electrons, it will there is a very small increase in the size because the due to the poor shielding effect, the outer electrons are directly attracted with the nucleus, and due to this, the attraction increases as thus, we can say that there is a decrease in the size, right? Or we say there's a very small increase in the size from AS to BI as compared to Na to AS, right? So from Na to AS, there is a large decrease in the size due to increase in the number of shell. But when you move from AS to BI, there is a very small increase in the size, right? Almost remain constant. Now, what oxidation state they basically show the group 15 elements. So they have either two options. Either they accept free electron to become stable or if they octet, so it will show -3 oxidation state, or it have also option like it will form five bonds with the someone except nitrogen, right? So they also show +5 stability. And if I'm talking about the out of +5 and +3, which stability increases down the group? So +3 stability is increased down the group due to the inert pair effect. That is what is the inert pair effect? That is non-participation of NH2 electron in the bond formation. So as we move down the group due to inert pair effect, these NH2 electron are non-participation in the bond formation because they are due to poor shielding effect. These NH2 electron are attracted by the nucleus, and thus these two electrons are not available for the participation in bonding. Participation takes place, right? So these due to this +3 oxidation state increase down the group as compared to the +5 oxidation state, right? So one important note here: nitrogen always show 3 oxidation state. It will not show +5 oxidation state due to the absence of vacant d orbital. And when you move down the group, the stability of the +3 oxidation state increase as a result of the inert pair effect. So I hope this is clear to you. Now, ionization enthalpy. So ionization enthalpy decrease from Ni to Bi as the size increases. Ionization enthalpy start decreasing. So there is no exception on this. So these are the some important points related to the nitrogen family or group 15 family. That is the member, atomic radii, oxidation state is very, very important. That is 3 and 5. T increase down the group and 5 decrease down the group. And nitrogen does not show +5 oxidation state because due to absence of vacant d orbital. So it does not have any d orbital. It having only 1 is to 2 is to 2p, 2p4 type. 1 is to 2 is 2, that is 4, and 2p3. So it does not have any 3d orbital. So due to the absence of vacant d orbital, it will not show +5 oxidation state as well. So I hope this is clear to you. Ionization enthalpy is simple. That is decrease from nitrogen to this one. Now, so the important compound here is nitrogen. So first important compound of this group is nitrogen. So how will you prepare nitrogen? Basically, the first question is, how will you prepare nitrogen? So basically, when you heat copper oxide with ammonia, right? So when you heat copper oxide with ammonia and heat it, then we'll get N2 plus Cu plus 3H2O. So this is how will you prepare N2. And the next one is by treating calcium oxychloride, that is a bleaching powder with ammonia. And when the action of heat, we'll also get the N2. Right. Now, when the ammonium nitrate is decomposed, it is decomposed to give H2O and Cr2O3, right? And N2. So this is also will get the N2 as a product, right? So these are the way by which you prepare nitrogen. So what are the properties of dinitrogen? So basically dinitrogen are very, very stable. They form triple bond with each other and quite stable at room temperature, right? So they are almost unreactive due to their stability. However, they react in some cases like a formation of nitride. So with a very reactive metal like lithium, magnesium, calcium, and ammonium, calcium, they are very reactive metal. Alkali metals, when they combine with N2 and heat, it will form calcium nitride. Similar way, on lithium also form lithium nitride, right? For example, all of the other element of this group, that is potassium, sodium, it cannot form nitride, but lithium is the only element of group first alkali metal. It will form lithium nitride directly. Now, oxidation. So when the N2 is treated with O2, it will form 2N, right? So it will form nitrous oxide. Reduction with carbide at 1273 Kelvin. So when the calcium carbide is treated with N2, it reduction takes place and it will be converted into calcium cyanide, right? So this will the formation, or we say the reaction with the carbide. So these are the properties of dinitrogen. The first one is formation of nitride with the LiMgCa and Al, right? And the oxidation with the N2 and O2, it will give 2NO, and reaction with carbide to give CaCl. Now, these are some oxides of nitrogen, as we can say that this play a very, very important role. So, if just for this, I'll put the table here so that you can learn this thing easily. Now, the first formula of oxides of nitrogen is that is N2, right? So N2, so N2 having the resonance diagram like this, that is N, N, and O, and also like this, that is N, N triple bond and O. So here the bond parameter is like 133 picometer. If I'm talking about the bond length of N, it will be 113 picometer, where the bond length between N and oxygen is nothing but 119 picometer, and its shape is linear, right? Its shape is linear, that is N2O. Similarly, we'll draw the structure of NO. So NO, we have a structure like this, that is N double bond, a lone pair of electrons, right? So this will form 2 to 4 to 6 electron, right? 2 to 4, and this one, this oxygen, that is a 2 to 4 and 1, 5, right? So this is the structure of NO, right? So I hope this is clear to you. Now, NO having the bond length of 1.5 picometer. So how will you how they will make bond with NO? So how will you draw the diagram of NO actually? So we know that N having electronic configuration 2 comma 5, oxygen having electronic configuration 2 comma 6, right? So NO having a structure like this. O wants two bonds, so these two bonds is like this. Now, out of these two bond, one bond is right. One bond is like, because oxygen, we all know oxygen having six valence electron. So out of this six valence electron, they were two to four, right? And here oxygen have a five valence electron. So out of this five valence electron, one lone pair. So it having three lone pair of electrons. So these two bond consist of three electrons of nitrogen, right? And one of, two to four and one five. Two to four and one five. So one electron of in this two bonds, right? So in this two bonds means how many electrons? Four electrons. So out of this four electrons, three electrons of nitrogen and one electron of oxygen is present, right? So three electrons of nitrogen is present in this and one electron of oxygen is present. So this is the structure of NO. So this will also show resonance in which the three electron of oxygen. So they will also form like a structure like this, that is N. They having a structure like O, 2 to 4. And this will also having 1 and 2. So here also we can say that nitrogen will be 5. So two electrons of nitrogen and two electrons of oxygen will participate in this. So it will also form a structure like this, right? So these two possibilities are there. So this two have a resonance diagram of NO. Now, so this is the resonance diagram of NO. Similar N2O. So we have a resonance diagram of N2O is like NN, and this will form the bond like NN. This will form a single bond, right? Here double bond means the one is a coordinate bond of nitrogen, right? So this will be the N2O NO. Now let's see, draw the structure of N2O3. What is the structure of N2O3 basically, beta? So this is the structure of N2O3, like NN, and this will be O3, right? So they having a double bond, N2O3, this having a single bond, this also having a double bond. So these two having a double bond, these two having a coordinate bond. So how will you define this coordinate bond? We know that nitrogen having five valence electron. Out of this, two electron are consumed here, two electron consumed here, that is four, and one electron consumed here, that is five. Again, this nitrogen consists of five electrons out of two electrons consumed here and one electron three, that is two, it remains as a lone pair. So this is how this will form, right? Again, here also they will form the, right? This will form as a lone pair of it, right? So total we have a two resonance diagram, out of which we have to draw the diagram like this, right? So this NO bond length, that is NO bond length is nothing but 105, and this NO bond length is nothing but 121 picometer, right? So these two, those having a single bond, right? Coordinate bond are longer than the double bond, right? They is having a 121 picometer, and the bond length between the nitrogen is nothing but 186 picometer, right? I hope this is clear to you. Now, this is the diagram of NO2. So how will you draw the diagram of NO2? So diagram of NO2 is like N, right? N having the positive charge making bond with the O2, and this will with O. That is a coordinate bond. Okay. NO2 structure is like this. That is O, and this is O. So this will form double bond, and this will form the coordinate bond. So it will be like they will releasing two. Just wait, just right. So this having a two electrons and two electrons. This is fine, and this having six electrons, because here the coordinate bond is formed. So nitrogen having two and two four. So they are left with the one electrons only. Right. So this is the structure of NO2. Okay. So NO2 angular structure and bond angle is 120 picometer. Next is N2O4. So N2O4, we also have a diagram like this, N2O4, right? And the N2O5, we have a oxygen are linked between these two nitrogen atoms. So these all are the oxides of nitrogen, and their reference diagram, and they are the bond parameters. So this play a very, very important role, right? So just try to understand this thing, because many times questions were coming related to this resonance structure or the bond parameter itself. So if you know this thing, then you can easily, calculate this value. So what are the oxy acids of nitrogen? So we already discussed about the oxides of nitrogen and the properties of dinitrogen. Let's see the oxy acid of nitrogen, right? So oxy acid, like when the basically nitrogen is combined with the hydrogen and oxygen, it will be called oxy acids of nitrogen. So oxy acid of nitrogen is like H2N2O2, also known as a hyponitrous acid, H2NO2, also known as a hydronitrous acid, HNO2, that is a nitrous acid, HNO3, that is a nitric acid, and HNO4, that is a pernitric acid, right? So this is how will you actually classify oxy acid and the name of their oxy acid. So H2N2O2 represent hyponitrous acid. H2NO2 represent hydronitrous acid. So remember this, H2N2O2 hypo and H2NO2 represent hydronitrous acid. Similar, HNO2 represent nitrous acid, HNO3 represent the nitric acid, and HNO4 represent nothing but nitric acid, right? So this is all about the oxy acid of nitrogen. Now, preparation of ammonia, that is how will you prepare ammonia, because ammonia is the important compound of group 15 element, very important compound, ammonia. So first of all, by heat, how will you prepare ammonia, beta? So by heating ammonium salt with the strong alkali ammonium chloride treated with NaOH, it will form ammonia gas. So this is the first way by which you will prepare the ammonia. How will you prepare, beta? So you will prepare ammonia by heating ammonium salt with a strong alkali, like ammonium salt, like ammonium chloride. When they are heated with the NaOH, it will form NH3, right? Again, by the hydrolysis of magnesium nitride, we can also prepare. By the hydrolysis of magnesium nitride, like Mg3N2 and 6H2O, we can also prepare MgOH2 plus 2NH3, right? So this is the way by the prepare magnesium nitride. So when the magnesium nitride is treated with H2O, it will form magnesium hydroxide plus NH3. Similarly, Haber process, we have also one process like a Haber process by which you can prepare ammonia. So in the Haber process, basically when N2 react with 3H2, it will form 2NH3. So what are the conditions for the Haber process? So basically in Haber process, we can say that this is a 1 mole of the gas and 3 mole of this gas. So total number of mole, we have a 4 mole. N2 plus 3H2, right? So we have a 4 mole of gas. And here we have a 2 mole of gas. So in the product side, we have a less mole of gas, and reactant side, we have a more mole of gas. So for this high pressure, so if you increase the pressure, so according to the Le-Chatelier principle, if you increase the pressure, then equilibrium is shifted in direction where less pressure is present. So less pressure is in product side. So this reaction proceed into the product side. So for this reaction, high pressure and low temperature is required. Why the low temperature? Because this reaction is already exothermic. It emits some energy as well. So they emit some negative energy, right? So this reaction is exothermic. So for such reaction, that is for the preparation of ammonia. This is the industrial method for the preparation of ammonia. So in industries, we basically prepare ammonia by using this method only. So what we do, how will you prepare by this method, beta? So we will prepare by this method. So what are the important or desired condition? So the desired condition is like high pressure and the low temperature. So these two are the desired condition for the preparation of ammonia by the Haber process. Right? Now, let's see some the properties of ammonia. Right? Some properties of ammonia like basic nature. So first of all, its aqueous solution is basic in nature and turns red litmus into blue. So first of all, it indicates the basic nature. How? When because the aqueous solution of ammonia in basic nature turns red litmus into blue, and it clearly indicates that they are basic in nature. Right. Similarly, reaction with the halogen. So this play a very important role. Remember this formula because many times question were asked from this property that alone. Right. That is what happened when the uh, ammonia react with the halogen. So basically reaction with the halogen, like when the NH3 is react with the Cl2, it will form ammonium chloride plus N2. Similarly, when the NH3 is treated with the Cl2, it will form NCl3 and 3HCl. Similarly, NH3 is treated with the Br2, it will form NHBr, NH4Br and N2, right? Similarly, NH3 is treated with Br2, it access, it will form NBr3. So always remember this thing. When NH3 is treated with Cl2 alone, it will form ammonium chloride. When NH3 is treated with excess of Cl2, it will form NCl3. Okay. Similarly, when the NH3 is treated with Br2, it will form ammonium bromide. But when excess of Br2 is taken, it will form NBr3. Similarly, when it's treated with I2, it will form ammonia, NH3 and I3 plus 3HL, right? So these are the reaction with the halogen. So very important reaction. That is what happening when the ammonia is treated with halogen. So always remember whether it will ask in an axis or in the whether in the chlorine is an axis, bromine is an axis, or ammonia is an axis. So always remember that. Whenever ammonia is in excess, then it will form ammonium chloride, ammonium bromide, and ammonium iodide like this. Whenever chlorine or bromine is in excess, it will form NCl3 and NBr3. So remember this point. These are very, very important. I hope this is clear to you, right? Good. ठीक है चलो. So now we study complex formation. That is what happened when they are treated with like this, right? So complex formation, like when the Ag is treated with NH3, it will form AgNH3 twice plus. Similarly, when the copper plus is treated with NH3, it will form copper ammonium complex, right? Similarly, with the Cd, it will form the cadmium ammonium complex. So basically, ammonia will form complex formation. When they are treated with the silver, it will form the silver complex. Similarly, when they are treated with the copper, it will form tetraammonium cooperate, and similarly with the cadmium it forms the complex, right? So these are the complex reaction of the ammonia. So ammonia is able to form the complexes. Why they form complex specifically? Because here we can see that and having the lone pair of electrons, so they will coordinate this lone pair with this Ag. Basically, with the transition elements metal, the complex formation takes place. S and P block do not make complex, right? Except lithium, no alkali metal will form the complex formation. So while they are d block elements form complex formation due to their vacant d orbital and their vacant d orbital variable oxidation state, they will tendency to form complex formation. Now, precipitation of the heavy metal ions from the aqueous solution of their salt. Basically, FeCl3, when they react with the ammonium hydroxide, it will give FeOH3 brown precipitate, right? It will give FeOH3 brown precipitate and ammonium chloride. Okay. Similarly, when the AlCl3 react with the ammonium hydroxide, it will form white precipitate. Right. So whenever the FeCl3 is treated with the ammonium hydroxide, it will form brown precipitate. Whenever the ammonium chloride is treated with ammonium hydroxide, it will form which type of? Yes, it will form, right. It will form white precipitate. But when the chromium chloride is treated with ammonium hydroxide, it will form green precipitate. So always remember this thing. It will form green precipitate. Now, let's see some phosphorus. That is the allotropic of phosphorus. So we have three types of phosphorus with us. That is the white phosphorus, red phosphorus, and the black phosphorus, right? So these three types of phosphorus we have. If I'm talking about the white phosphorus, it is a translucent, white, waxy solid, extremely reactive and poisonous and insoluble in water. So just remember this property: translucent, white, waxy solid, extremely reactive and poisonous and insoluble in water. Red phosphorus, So they are formed by heating white phosphorus in the absence of air. Does not burn spontaneously at the room temperature, right? So they are formed by heating white phosphorus at the in absence of air. Now black phosphorus, they form further heating of the red phosphorus. So always remember these three in a sequence only, right? That is a white, red, and the black. So white phosphorus, red phosphorus, and the black phosphorus. So white phosphorus, they are translucent white salty salt, extremely reactive and poisonous and insoluble in water. Red phosphorus, so they are produced by the heating of the white phosphorus, and the black phosphorus is produced by the heating of the red phosphorus, right? So always remember white, red, and black, right? White, red, and the black. Okay, these are the structure of this. We can observe that this is a P4, right? This is a P4 molecule. This is a this have a P2 and we have a P2 and P6, right? So these are the structure of the white and the red phosphorus, right? So these are some important compounds of the phosphorus. Like first one is the phosphine. So phosphine is a very important compound of the phosphorus because phosphine play a very important role in the manufacturing of many important things. So how will you prepare phosphine? So basically we prepare phosphine by treating with the calcium phosphate. Right, when the calcium phosphate is hydrolyzed, it will produce phosphine. Similarly, S3PO3, the oxo acid of phosphorus, it will also produce a PH3. PH4I react with KOH to produce this, and the phosphorus, that is the white phosphorus, also react with this to form this, right? So formation of phosphonic iodide, that is PH4I. So what are the properties of phosphine? That is the formation of phosphoric iodide. Similarly, combustion of PH3, it gives us S3PO4. And how will you prepare phosphorus halide? Like when the P4 is treated with Cl2, it will form PCl3, or we treat P4 with the 10Cl2, will look for PCl5. So then the preparation of phosphorus halide, so phosphorus halide can also be prepared from this P4. So when the P4 is treated with Cl2, or either thionyl chloride SOCl2, you will get the phosphorus halide, right? The property of phosphorus halide, whenever the PCl3 is treated with water, it will form oxoacid of phosphorus like S3PO3, POCl3. Whenever they are treated with the silver, it will form AgCl precipitate. SN, therefore, SnCl4. When they are heated, it will decompose into PCl3 plus Cl2 because these two Cl2 bonds are present at the equatorial position, axial position, and they are unstable. Due to this, they decompose to give this, right? So these are the oxides of phosphorus. Like when P4 is treated with O2, it will form P410O. When the P4 is treated with Cl2, it will form PCl5. Whenever the P4 is treated with Cl2 it will form PCl5 again. Now, when the P4 is treated with O2, it will form P4O6. Again, with H2, it will form H3PO3. Now, P4S2 treated with H2, it will form H3PO4. Again, HNO3, it will form N2O5. Again, with H2SO4, it will form SO3. Again, with the Cl3PO form H2S3PO form. So this will the oxides of the phosphorus, right? So these are the oxides of phosphorus, and these are the oxo acids of phosphorus, right? So these are the oxo acids of phosphorus, like hypophosphorus acid, phosphorus acid, hypophosphoric acid, orthophosphoric acid, pyrophosphoric acid, metaphosphoric acid, and all. So this we are going to discuss. So we already covered this all group 15. So from group 16 that we are cover group 16 in the next class. So today we are covering group 13 of the periodic table, group 14 and group 15. So we already covered group 3 groups today, that is group 13, 14 and 15. In tomorrow class, we are going to cover group 16, 17 and 18 and some PYQ question of this chapter, right? So I hope you like this, and we already cover all this topic, important topic related to this chapter. So just revise this concept, just divide this PDF or PPT. If you get this thing, if you remember this thing, then you can easily solve question related to this, because it's all need that how you keep focus on these points and how you remember this point. If you know this point, you understand this concept, if you remember the point, then you can easily solve the question related to this topic, right? So let's meet in the next class tomorrow, and we are going to discuss some important things related to this chapter. Till take care, and just do this. You can get and you can able to solve such questions, right? So let's meet on the next class.